All right, here we go. So this, honestly, I don't think there's a single thing in this video that's new. This is just really intended to be a super quick refresher on basically Newton's first two laws. Okay, so if you are 1000% sure you remember everything there is to know about Newton's first two laws, don't even watch this. Or if this is too fast and you need more of a refresher, then please, please, please go back and watch the honors videos. Okay. So Newton's first two laws, here we go. So first of all, remember a force. When you measure a force, you're measuring how hard you are pushing or pulling an object. Please remember it is a vector, and so it has direction. All right. We will usually use units of newtons to measure how hard the object is being pushed or pulled. All right, some common examples of forces that we're going to talk about are things such as the force of gravity, pulling an object down, the force of a person, like the force of Roy, the normal force, okay? Now, remember, this is a quick reminder. Normal force always act perpendicular to the surface, okay? So let me show you that real quick. Why can't I? There we go. So if you've got an inclined plane with a box on it, your normal force always acts from the surface of the box and points up. All right. Technically, last year we were drawing them like this, right, where the arrow came out of the box. This year I'm going to try to be a little bit more careful about drawing the force at the point of application. Okay. But notice this is in fact perpendicular, and no matter which way the ramp is facing, oops, that's not what I'm going to do. No matter which way the ramp is facing, that'll always be the case. So even if the wall is vertical, it's still perpendicular. Maybe for some reason the box is on the ceiling, then the normal force pushes down, right? Maybe, maybe Roy is pushing the box up, and the normal force and gravity are both pushing down. Okay. So anyway, your normal force is always perpendicular to the surface. All right. And this, as we're going through the problems, we're going to run into all sorts of weirdness with which way your surface is facing. Okay. Let's see. Tension is the force exerted by a rope or a chain or whatever. In a lot of ways, it's similar to normal force, right? Because it sort of supports your object. If you've got a spring, let's see what we do here. We did tension force. Force of a spring is the force exerted by a spring. All right. And then friction. All right. Anytime two objects rub or try to rub against each other, friction will oppose the attempted motion. All right. At the beginning here, all our friction stuff is going to be real simple. Video, I don't know, 4.3 or 4.4 or something is about the two types of friction. We'll review that. And then finally, drag force is the force of air resistance. The drag force is pretty complicated, all right? It says here we're going to talk about this more in a few days. That's actually a lie. We're going to do everything about drag force at the end of the year after you guys have a little bit more calculus under your belt, okay? So, there we go. All right, let's see, what else do we need to know? Couple important things to remember about forces. First of all, remember, force measures how hard the object is being pushed and has absolutely nothing to do with how fast the object is moving, okay? That is a common mistake that people make, is they confuse how hard the thing is being pushed with how fast it's moving. Remember that just because you've got a force on an object doesn't mean it's moving. And furthermore, it's possible to be pushing an object one way while it's moving the other way, right? Like last year, we kept talking about the Superman example, right? So here's the ground. Here's a school bus that's, sliding across the ground, right? And there's a baby over here. There's our baby. Oh no! Ah, right? And then Superman wants to save the baby. So rather than just moving the baby, Superman decides to stop the bus. Right? And so the idea is the velocity of the bus is this way. Notice where I drew my velocity vector. And the force from Superman is this way, right? Okay, so just because the force is in a certain direction does not necessarily mean that the motion is in that direction, okay? What this does mean is my net force is going to be negative, which means my acceleration is going to be negative, which means that my velocity is going to decrease, right? Okay? Let's see, what else? Remember that force includes direction, right? We talked about that it's a vector. So in this example here, Superman's force would be a negative force because it's in a negative direction. We don't need to distinguish between push or pull. All we care about is what direction the object is being pushed or pulled. Okay, so this is all hopefully review and just intended to reignite some of those ideas that we learned about last year. All right, the most important thing you can talk about for an object when you're talking about forces is the net force. All right, and last year we almost exclusively used this notation. Occasionally we use this notation, but it's the total of all of the forces on the object. All right. There's a principle, this is actually something we didn't learn last year, called the principle of superposition for forces. And it says that a net force has the same impact as a single force with identical magnitude and direction. In English, what that means is this. If you've got a box with a whole bunch of forces on it, maybe you've got whatever, 10 newtons this way, and 3 newtons this way, and maybe you've got, I don't know, about, let's do 8 newtons this way. That is, as far as the box's motion concerned, as far as the box's motion is concerned, it's the exact same thing as if you just had 1 newton this way. Okay, this is a 1, not an in. Okay, because over here your net force is -1 newton, and over here your net force is -1 newton. Okay, so both, as far as the motion of the box is concerned, both figure A and figure B are the same. Okay, that's called this. Principle of superposition for forces. All right. Cool. Free body diagrams. We will be making zillions and zillions and zillions of free body diagrams this year. All right. So remember, when you make a free body diagram, you have to pick one object. Okay. Usually it's a box or something that's being pushed, up a ramp or something, right? Technically speaking, you're supposed to draw your body as a dot. Okay. And I'll talk about that more later on. I always like to use a box just because A, it gives me a little bit more visual, B, it gives me space to write down the mass. But on the test, on the AP test at the end of the year, they're usually going to expect you to, instead of drawing a box, they'll expect you to draw a dot for the object. Okay. The only forces we care about are the forces that act on that object. So if we're talking about pushing a box, all we care about are the forces that are on the box. We do not care about the forces acting on the person, right? So like, we know Newton's third law, right? If I push a box, the box pushes me. But usually what we care about is the box, and thus all we care about is the force of me pushing the box. Let's see. When you make your free body diagram, you got to draw all of your forces individually. Don't try to combine them in any sense. Draw your forces as vectors with the tails on the object and pointing out, right? So remember that if Superman pushes a thing, we don't do this. That's no good. We instead do this. Okay? Arrows always point out of the object. And I guess technically it should really be this. There's your object, and here's the force of Superman. Okay, so this is the very best one, right? Okay? All right. Remember that you always need to think about your coordinate axes. All right. Oh, here's a thing. I remember my students struggled with this last year. Coordinate axes can be shown. We don't always use X and Y. Let me talk about this. This is huge, actually. And if anybody watches this video, will you remind me to emphasize this in class the next day? Okay. Here's the deal. How do you know what direction your axes go? All right. So you always want to choose your axes. That's not axes. It's the plural of axis. Such that one axis is parallel to the acceleration. Okay. The best example I can think of this where this comes up, and I'm totally getting ahead of myself, but it's probably worth talking about, is this. So ordinarily when we do inclined planes, instead of doing the usual X and Y axes, what we do is we take those and we rotate them so that we instead have a parallel and a perpendicular axis, right? Okay, but there are going to be times this year where our object will have, so here's the simple example. So imagine this is a car going around a corner or something, okay? So let me get rid of all this stuff that I just drew. All right, so here's a car going around a corner. So this is the front of the car. So here's our driver. He's driving out of the screen, right? Here's the wheels, headlights. Okay, so the car's driving towards you right now, and it's driving around a curve that is banked. Okay, so the car is actually going to go around in a circle like this. Okay. Well, in that instance, hopefully the car is not going up or down the ramp at all. All of the acceleration would be centripetal acceleration, right? And centripetal acceleration always acts towards the center of the circle, okay? And so in a scenario like that, even though you're on an inclined plane, you still want to use x and y axes, because that way your acceleration is in the direction of one of your axes, okay? So, anyway, that's probably getting ahead of myself, but that just occurred to me as I was doing this here. All right, so anyway, so you have to think about your axes. I guess that's the point. All right, this next point is another one that's pretty big this year. So technically speaking, when you draw a free body diagram, you're supposed to show the actual forces, not the components, okay? And in terms of problem solving, making a free body diagram with the components is more helpful, all right? So as we ramp up towards getting ready for the AP test, there are going to be problems that say, make a free body diagram. So what I always do is I make a free body diagram with the components, and then at the end, after I've kind of figured out everything, then I go back and make a free body diagram with the actual forces, okay? More about that as we get into it, all right? But just know that that's going to be a thing, okay? Any other information is always written off to the side. The acceleration should be written off to the side. The velocity, if you know any information about that, should be written off to the side. The only thing that you put on it are the forces on the object, okay? All right, so we talked about that, we talked about this, talked about that. Here we go. Sometimes we're gonna make free body diagrams for a system. All right, we'll deal with that a little bit later on. But just a quick reminder, a system is one or more bodies. You need to make sure that you distinguish between internal and external forces. Okay, where this came up last year was we did stuff like this, where we had, you know, like a block, or a ramp rather, with a block and like a pulley, right? And so you'd have a rope that ran up over the pulley and hanging down, and you'd have another block here, right? Okay, and so our system would be the two blocks and the rope, right? Okay, so external forces would be gravity pulling this block down, gravity pulling this block down, but you wouldn't worry about the rope because it was sort of part of the system, right? So you didn't have to worry about your tension force. So just remember that that was a thing, that we could look at free body diagrams for a system. You could also, if you wanted to, and usually needed to, in addition to that, make individual free body diagrams for the individual objects, right? So, you know, the box on the ramp would have gravity pulling down and the tension pulling it up. The box over here would have gravity pulling it down and the tension pulling it up. If there's friction, that would affect this drawing and this drawing, right? Because that would be external. Okay, so that's a super quick review. Again, we'll sort of build up to solving problems that are systems. So I wouldn't freak out about that yet, but just getting the ball rolling, all right? We're going to focus on Newton's 3 laws of motion. I don't know that there's anything here that's super important. Some history that I never spend time on because, frankly, I don't really, I never felt like I was good at teaching history, I guess. So, I don't know, you can read about the history of Newton at your leisure when you have time for it. Okay, Newton's second law, here it is. Net force, here it is. The acceleration of an object is directly proportional to the net force on the object and inversely proportional to the mass. The harder you push it, the bigger the acceleration. The bigger the object is, the smaller the acceleration. Okay? We will, this year, very, 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 very frequently solve problems with the silly equation, net force equals net force. This is our jam this year, all right? We're going to use this all the time. Net force equals net force. Here's what this means. The net force acting on an object is equal to, well, if you rearrange this, this is the exact same thing as saying net force equals mass times acceleration, right? This is the way Newton's second law is usually stated in books, okay? So we will very, very frequently solve problems using this. Net force is equal to the mass of the object times the acceleration. It's also equal to the total of the forces. So force 1 plus force 2 plus force 3 plus whatever, okay? And so what will happen is we've got all these forces, a mass, and an acceleration. Most of the problems are set up so that we know all of these quantities except for one, okay? So you will see me solve problems like this a lot, all right? And so I will refer to that as solving a problem using net force equals net force. And I'm just saying there are two representations for net force, mass times acceleration or total force, okay? All right, let's see, what else? Oh yeah, did I even talk about Newton's first law? Did I skip that somehow? Newton's first law, object in motion stays in motion, object at rest stays at rest, unless acted on by some sort of outside force, right? I think I talked about that. Weird. Okay, well, anyway, Newton's first law is covered by the second law, right? Newton's first law basically just says if your acceleration is 0, your net force is 0. Okay? So that is huge. I'm a little surprised that it's not in here somewhere. Mass. Oh. All right, well, anyway. Cool. You know what? I need to write it down. So here's the first law. The first law says these three statements are equivalent. If your net force is 0, then your acceleration is 0, and your velocity is constant. That's the first law. If one of those things is true, they're all true. If one of them is false, they're all false. Okay? All right, so mass, remember, is a measure of how much inertia an object has, right? The more inertia it has, the less it will accelerate under a given force because it has more resistance to a change in motion. All right, so the terms mass and inertia are somewhat interchangeable in this class. Okay. Let's see, what else do we need to talk about? Second law, we talked about that. Oh, remember that the acceleration is always in the same direction as the net force, right? If you've got a box and your net force is this way, then your acceleration will also be that way, always. Okay? So watch your signs there. I don't know if we need to worry about inertial frames of reference. I think I'm going to skip that. Oh, now here's the first law. Why is that there? I don't know. All right, so here we go. An object at rest stays at rest. Object in motion stays in motion, unless acted on by a net force, right? Because you need that net force to change the velocity. Here's those three things that I just wrote on the board a minute ago. I apologize for not having a better handle on my slides. Cool. Please remember that having a net force of 0 doesn't necessarily mean that the object isn't moving, right? Net force is 0 means your acceleration is 0. That means the velocity is constant, but not necessarily 0, right? Your velocity could be any number as long as it's constant, okay? And these are all or nothing. They're all true or all false, okay? So remember that in general, you need a net force to change the velocity of an object. If you want to get something moving or speed it up, you need a net force. If you want to stop an object or slow it down, you need a net force. You need a net force to make an object turn, but not to keep it going straight. Remember not to make the mistake of thinking that if an object is moving, there has to be a force on it. It's possible for an object to move at constant velocity if there's no forces on it. And finally, remember there are two ways to find net force, right? That's what I was talking about here with the whole net force equals net force, right? You can find your net force by doing mass times acceleration, or you can do it by adding up all of the forces on your object. Okay? This is going to be our jam for the next probably 3 chapters, okay? So, there you go. Super quick crash course. If that was too fast or too rambly, please, please, please go back and review those honors videos, okay?